Hi friends, back with another video. In the last part of the video, we have developed a, a study flow model for this reach. In this part of the video, we are going to model the internal boundary conditions. That is, we are going to model some inline and lateral hydraulic structure along this river network. So if you find this cross section, the number of, if you compare this number of cross sections to this last video where I have developed a simple 1D steady flow model, so the major difference you can find is the here I have added more number of cross sections. So more number of cross sections because I'm going to add the hydraulic structures, and another one major factor would be in upcoming video I will develop unsteady flow model for the same set of hydraulic structures for this river reach. So that's why I have created a more number of cross sections for the unsteady flow simulation. So it will help us to both the adding more number of cross section adding help us. One is to build a stabilized model. So if you look at it, so here I have marked tentatively marked the location of the weir. So approximately at this location I'm going to model a weir. For culvert at the downstream, at this location I am going to model a culvert, and bridge at this section is the intermediate part of the channel, and dike along these cross sections. This one is the dike. So let's move to HEC RAS geometrical editor and add all these structures in our model. Here you can see this culvert section, and you can see the circular rings. These are the culvert barrel, and the lowest point of the culvert barrel where the elevation are referred as the invert level. So this is the lowest point of the barrel, and this the levels which is taken at this level points are the invert level of the culvert barrels. And this one is the top view of this culvert. When if it is a square edge embankment, it looks like this, and if it is a sloping, you can see this. And this one is the side view of the square edge culvert, and this one is the sloping embankment. How is this square edge? So major thing we need to bear in our mind in the culvert modeling in HEC RAS 1D is the location of the placing the location of the cross sections. So suppose this one is the exact culvert location is this one, and here you can see I have marked two cross section. One is at the immediate upstream and one at the immediate downstream. So whenever you model a culvert, so if suppose this one is the location of the culvert, and in the 1D always mark a immediate upstream cross section and immediate downstream cross section. Okay, and on the previous cross section to the upstream should be marked at sufficient distance, because when the flow from this upstream which is the cross section previous to upstream, when the flow comes, it actually contract at this opening of the barrel, and thereafter it expand when it is flowing through this barrel and exits to this tailwater. So there will be expansion of the flow. So we should whenever you marking this upstream, the cross section previous to upstream and previous to downstream, we should mark at sufficient distance, and major care should be taken mainly for this expansion cross section. So we need to provide some expansion to this flow. So we should mark this downstream cross section at at sufficient distance to allow the expansion of the flow, and same methodology is applied for the culverts and the bridges. So this we should take care in our modeling for 1D models. For 2D, there is no need of consideration of this expansion and contraction zone. And let's move to this HEC RAS geometry. So if you look into this cross section 1183, this is the immediate upstream cross section of the culvert. So here is the upstream cross section, and at a distance of 3 feet from this upstream, I am going to which model a culvert. So that means at the station 1180 is the culvert location. So to add that culvert location, just move to add bridge or culvert options, add the stations where I'm going to model a culvert 1180, which is nothing but 3 feet away from the upstream cross section, that is the immediate upstream cross section from the culvert. So here is the upstream cross section and here is the downstream cross section. So this upstream cross section resembles the cross section 1183, and this downstream cross section of this river resembles this cross section 1147. Is the downstream cross sections. Now time to add the road deck. So for the road deck, it asks for this distance, enter the distance between the upstream cross section and the deckway. So we need to enter the distance, at what distance the culvert is at located from the upstream cross section. I already mentioned it is at 3 feet, and the width of this roadway deck. So for the roadway depth, the width of the deck is nothing but the length of the culvert barrel. So I will say the length of the culvert barrel is 30 feet, and it the curve this wear coefficient. This wear coefficient I assigned 2.6. My assumption is that I would say this condition at the site is that it's a uh, it's a roadway embankment which is having height more than 3 feet. So that's why I considered this wear coefficient as 2.6. So you can refer this HEC RAS manual to find to get this data based on these roadway embankment conditions. So now move to this uh, upstream, downstream. You can see this high chord and the low chord. So what is that high chord and low chord? So we can check that here. So if you can look into the sketch, so this one is the roadway deck, a typical roadway deck, and here you can see this is the downstream point and this is the upstream point, and the high chord is the highest point of the roadway embankment. So if it is a bridge, it is a for the bridge it is a deck, and for the culvert it is a roadway embankment. So here if you see, the high chord is the highest point of the roadway, so it is at here, and for the if it is a bridge, the lowest point would be the total height of the roadway deck. So it total depth of the roadway deck. So it comes somewhere here. Since it is a culvert, so we should consider it as an embankment. So for the embankment, this low chord extend up to this bed of the river. So it is set here, or you can call it as Talweg line of the streams. So it expands up to here, and this width of the roadway deck, um, as I mentioned earlier, and I assigned the data, I assigned the values. So I assigned that the roadway deck width is nothing but it is at 30 feet, so which is nothing but approximately equal to the length of the culvert barrel. So here is the I shown you in the perspective view how it looks if we add this culvert barrel here. So this length is nothing, is approximately equal to the length of the culvert barrel. Okay, and here is I have these values. I will just copy it and paste it there. is upstream and downstream. Just copy that value. Here you can see the upstream embankment side slope and downstream embankment side slope. I consider it as a 0. So if it is a 0, then it looks like this square edge. So which is, it looks like this from the top. So there is a, the slope is 0, so there is a square edge. All right. And it's a broad crusted weir. So for OJ weir, so it looks like this. So these factors affect in this model when the flow from this culvert barrel overflows over the top of the embankment. So when the flow from the culvert exceeds this top of the embankment, then it solves these weir equations to find the what is the quantity of the discharge which is flowing through this weir when the culvert overflows. Okay, all right. Now time to add the culvert opening. So culvert openings here. Okay, so here it asks for the type of the solution. So before that, so we here it asks us for these flow conditions. So we what kind of flow, what kind of a these conditions we are going to design model a culvert. Is it a invert control or a outlet control? So before that I will add these other parameters and let you know which conditions would be much better for this for particular conditions of this culvert barrel. So here I will consider this, I have this size for the culvert, it is, so here I will add these culvert parameters. So this distance to upstream is 3 feet, and the culvert length, it is length of the culvert is 30 feet. The entrance coefficient I will assign it as 0.6. Also you can refer this HEC RAS manual for this entrance and exit loss coefficient of the culverts. The Mannings at the top, this is the roughness of this culvert surface is concrete, and I will assign it as 0.13, and same for the Mannings at the bottom. And for the upstream invert elevation, I can move this, copy this value, paste it here, and for the downstream invert level of the culvert, just copy it, paste this value. Okay, I have this culvert length in feet, depth up to the bottom of the Manningsen. So this it is, you can assign this to if you want to consider a case of some obstruction at the upstream of the culvert. So here I don't consider that any obstruction or a blocked culvert opening cases. So I just consider normal case where there is no obstruction to the culvert flow against intervening the flow of the culvert. So barrel names, I will have this. So this is the central line stations of the culvert barrel. So here I am going to model a uh, seven culverts. So here is the culverts, the central line. So here is the central line of the upstream central line of the culvert and downstream central line of the culvert. So just copy these values and paste it there. So here is the openings, and so number of the openings, there are 7 openings of the culvert and culvert barrels, and its upstream center and the downstream station of this central line of the culvert. So it is like this. If I draw that same thing here, so this one is the culvert embankment. Yes, and it's a top view representation. It's a top view. So this one is the one culvert barrel. This one is the another culvert barrel. Another culvert barrel. Another culvert barrel. So this one is the roadway embankment, and these are the culvert barrels. So from this reference point, so if this is a point 0 station, and this one is I say station 100, this is the length along the color stations. So this is the length, so 0 to 100, and here is the stations. So this is the culvert center line. This is the culvert center line for each culvert. For this culvert opening, this culvert opening, this culvert opening, this culvert opening. So for all culvert opening, this is the center line. So for this one, this one, this one. So like that, we have considered the culvert openings and its stations from upstream to from left to right. Now diameter of the culvert, I have this one. Diameter of the culvert is 2 feet. This is nothing but the opening of the culvert. Okay, all the data are filled, and this one is the culvert is the concrete pipe culvert and square edge at entrance head wall. The square edge with entrance head wall looks like this if from the top view. So from if this is a culvert barrel, and this one is the embankment, roadway embankment, and this one is the head wall at the entrance. This is the opening of the culvert, and this one is the head wall at the entrance. So this entry conditions for the culvert affect these take care of the losses. So if it is a wing wall, there will be less turbulence of the flow, and more efficient compared to head wall. Head wall is okay, but the wing wall opening for the culvert is much better because it conveys the flow with the minimum turbulence. Okay, this is condition and also it depends on the site conditions. So square edge with head wall I have considered. This takes into account of the entrance losses in the culvert modeling. So the main thing which I have to about to tell you now is the solution criteria. So which condition I should model my culvert, whether it's for inlet or outlet control. So if you look into here, I have this upstream invert elevation and the downstream invert elevation, and I have this culvert length. I will calculate it here. Yes, here. So I will calculate the slope. I will calculate the slope. So I will calculate the slope for these culvert barrels. So upstream slope is, So there was a small correction for the downstream invert level, which I corrected it now. So now I will find the slope of this culvert barrel. Slope of this culvert, I have this slope is the difference between this and the length of the culvert. The length of the culvert is 30 feet. So into so that is the slope percentage 1.73. So 1.73 is the steep slope. So we can go for the inlet control here, because inlet control we can the main conditions of the inlet control is the barrel is going to, the flow in the barrel is mostly in most cases is the at supercritical flow. So that means for this situation the going for the inlet control would be much better compared to outlet control, because this slope of this barrel slope of this culvert is steep, that is the supercritical flow in this culvert. So that means inlet control satisfies for this condition. So inlet control, I will assign this as inlet control here, and it for the diameter I have it is 2 feet. So diameter is 2 feet, 2 feet, and here I will update those invert levels from here. Okay, it's still small, so it needs to be improved. So I will increase this culvert barrel size to 7 feet. Now I can improve some more. I will to 8 feet. Yes. Sorry, actual was 9 feet. Sorry. Here is the diameter of the culvert. I have I forgot to update, so I will update it here now. Actually, it was 9 feet. So it has to carry a large flow from the streams. Oh, sorry for this. Uh, hmm, Sorry for this. This is actually the correct one. The diameter of the culvert is 9 feet and 7 barrels we are going to model here. So now it is correct. So we have modeled the 7 barrels for this culvert, and now we have to make some areas of this culvert to be ineffective. That means it should not convey flow from this part of the cross section. So if you look into this, so this one is the embankment, or the gray zone of this culvert, where there is no flow will convey for this zone, because it is a embankment. Only flow will convey through these openings. So that means whatever these gray zones are there, so we will make it as permanently ineffective for these zones. Okay, So this is time to make it ineffective. Wherever these wherever the gray zone is there where the flow is not conveying, we will make it permanently ineffective areas. So we can do it by here. Move to that upstream cross section as it is the immediate upstream cross section of the culvert. Just move there, and I want to consider the multiple points at the multiple blocks I want to consider. So you can, I have this data, I can directly copy and paste it there. Let's see, control B. So here is the, here you can see the permanent y or n. So the permanent y or n, when you make it permanent, it will be that the these the whatever the location which is marked as ineffective will be permanently ineffective. When you assign it as a no, when the flow rise above that ineffective level, that in that case the ineffective area becomes effective. So that's why I'm making it as a permanently effective. Okay, so here you can see this these areas are becoming permanently ineffective. So these are actually these road deck part, or this embankment part of the culvert, where there is no flow will convey. The flow will convey only through these barrel openings of the culvert. So you can use this graphical, you can use this graphical cross section tool to edit it quickly. So since I already copied that location to save my time, so I have directly added it here. Save my geometry. For roadway, for contracted weir, so this is the location where I'm going to model a contracted weir. So that is the upstream of 3612. So it is between, it comes between 3612 and 3553, where I'm going to model a contracted weir, so which is the inline structures. So inline structures, I need to add that contracted weir here, and 3612. So assume that it is 10 feet. So it is the actual this actual contracted weir is at 10 feet away from this upstream cross section. So that means its elevation, it is at 3602. 3602, it comes the invert level 3602. Okay, this is the embankment section, and I assume no pilot flow. What else? Embankment distance is 10 feet, and the width of this embankment, this width of the weir is 25 feet. 25 feet. The weir coefficient is 2.6. Now the stations and its elevation. Copy it, paste it here. The broad crested type where the upstream slope, it is the embankment slope is 2 horizontal to 1 vertical, 2 horizontal to 1 vertical. The broad crested weir. So this is suppressed where we have modeled. Now, so for this weir, so we are going to make it the ineffective area. So only this opening part would be effective. Rest all this part would be ineffective. That is the gray zone where there is no flow will convey from this gray zone. The flow will convey only from this opening. So that's why I need to make it this as effective and the rest others as ineffective. Move to that cross section here. The upstream cross section to this where. So move to this ineffective area. There will be multiple blocks and it's a permanently ineffective area. You can copy it directly these values or you can do it manually, but to save time I'm doing it taking the copy and pasting it here. Okay, so this is the location where the would be ineffective areas which I marked here. So it is a contracted weir at the upstream. So you can even use this graphical editor tool, is the graphical cross section editor tool to quickly do that task. So you can select any, if you want to add any multiple blocks, you just select and drag it, you can add it quickly. Okay, so now we have added these two structures. One is the culvert and another one is the weir. So now we will add these bridges and the dikes.